The Lemke-Howson algorithm for finding Nash equilibria in two-player games moves around in the best response polytopes of the two players until it finds a fully labeled pair of points in those best response polytopes. But the problem is that the best response polytopes can be quite large, so you don't want to construct them up front and then move around in them. Rather, you want some more algebraic way of moving around in these polytopes without constructing the polytopes first. And this works via a process called complementary pivoting. We use our running example of a game again. We have player 1 that has 3 strategies, and we have a player 2 that has 2 strategies, which we call 4 and 5, and we have a payoff matrix for player 1 and a payoff matrix for player 2. And then we have the best response polytopes for both players. So first for one player, we can draw the best response polytope by looking at these inequalities that arise from the payoff matrix of the first player. So we have a constraint that says 3 times y4 plus 3 times y5 has to be at most 1. And that essentially divides the space into 2 halves. And all the points that satisfy this inequality lie below this separating line. And then we have a second constraint which says 2 times y4 plus 5 times y5 should be less or equal to 1. Again, that just separates the space into 2 halves, and all points that satisfy this inequality lie below this line. And then we have 6 times y5 must be less or equal to 1, so that just again divides our space into 2 halves, and all the points that satisfy this inequality must be below this line. And then we also know that y4 shouldn't be negative, and also y5 shouldn't be negative, and this essentially gives us a closed polytope. So we have all these 5 sides of the polytope now. I now want to rewrite these set of inequalities, and I essentially want to turn these inequalities into equalities. And there's a common trick here, which is to introduce what's called a slack variable on the left-hand side. So for example, in the first inequality, we just introduce a whole new variable to this system, the variable y1. And this variable y1 can be as large as we want, and so it can always make up the difference that the remaining term would have to the value 1. And so we can just now set this inequality to an equality. We can require that the left-hand side actually must be equal to 1. And this variable, the slack variable y1, has an interpretation. And the interpretation is that the variable essentially expresses the distance to the corresponding facet in this polytope. The first inequality defined this line that divides the space, and y1 is simply proportional to the distance to that dividing line. And we do the same thing for the second inequality. We introduce a slack variable called y2 and turn the inequality into an equality. And again, y2 just gives us a distance to this dividing line, number 2. And we do the same for y3, of course. And all of these new slack variables, y1, y2, y3, also have to be non-negative. Of course, we are in particular interested in these intersection points of these lines, these vertices of the polytope. And there's a nice property here, which is that the vertices of the polytope correspond to setting 2 of the variables to 0. In this case, these would be the variables y1 and y2. And there's another interesting observation here, which is, well, in this example, the point is adjacent to the labels 1 and 2, and those are exactly the variables that are set to 0. And this is always the case. So the variables that are 0 exactly correspond to the labels that are adjacent to that vertex. We call this a basic solution. Now, here's a way of how to keep track of our current basic solution. So say we want to express that we are currently at a specific vertex in the polytope, meaning two of the variables are 0 and the other variables have some positive values. Now, how should we express this? How should we keep track of this? The idea is to rearrange these equalities in such a way that all the non-zero variables are on the left side and all the zero variables are on the right side of the equality. Let's look at an example. So let's look at this point, this origin point where y4 and y5 are 0. Now that means we want y4 and y5 on the right side of the equalities and y1, y2, y3 on the left side. Okay, so we just move y4 and y5 to the right side, and we just leave y1, y2, and y3 on the left side. We just move things around. And let's clean this up a bit and remove these spaces. And now the result here is called a dictionary. There's one dictionary for each basic solution, for each vertex in the polytope. Okay? We do the same thing for the best response polytope of the other player. So if you remember, the flattened version of the best response polytope for the other player looked roughly like this. And then we can say, look at a particular vertex in that polytope. Let's say this one, where we have the labels 1, 2, and 3, meaning the variables x1, x2, and x3 are actually 0. So what would be the dictionary for that basic solution? Well, it would simply be x4 on the left side, because it's non-zero, equals 1 minus x1 minus 4 times x3, because x1 and x3 are 0 variables, so they should be on the right side. And the coefficients here just come directly from the payoff matrix of the second player. And then we also have x5 is equal to 1 minus 2 times x2 minus 3 times x3. Again, x5 is on the left because it's non-zero, and x2 and x3 are on the right because they are 0. And all the variables should be non-negative as well. Now, remember that Lemke-Howson moves around in these best response polytopes. We now have a pair of points where we start, and now we can decide to drop a label. Let's say we decide to drop label 3. What does this mean? Well, it means increasing the variable x3. It's currently 0, right? Which is why we have label 3. And we want to get rid of this label, so we have to increase the variable. Okay, so it's 0 right now, and now we will increase it. The question is, how much should we increase this variable? And there's a limit on how much we can increase it, because at some point, some other variable will become 0. And if then we would continue to increase x3, this variable would become negative. And we don't allow negative variables. So we have to find out which variable will become 0 first. There are two variables that are affected by the increase of x3. The first one comes from this first equality on the right side, x4 equals 1 minus x1 minus 4 times x3. If we increase x3 here, x4 will eventually become 0. When does this happen? I mean, maybe you can pause the video and try to look for it yourself. But it's actually quite easy. So we have these two equalities that involve x3. The first equality, which has x4 on the left side, has the property that the right side will become 0 once x3 is 1/4. And the second equality, which has x5 on the left side, has the property that the right-hand side will become 0 when x3 is 1/3. So 1/4 is smaller than 1/3, so x4 will actually become 0 before x5 does. And this is all we need to know. Basically what this tells us is if we drop label 3, what will happen is we will pick up label 4. And so this is just what we do. We know we pick up label 4, which is x4 becomes 0. And we just write a new dictionary for this new basic solution. Now, what does this dictionary look like? Well, x3 is not 0 anymore, so it should move to the left side. And x4 became 0, so it should move from the left to the right side. Okay, so we just swap x3 and x4. And then we have 4 times x3 on the left-hand side, which is not very nice. We just want the variable with no particular coefficients there. So we divide the whole equality by 4. And then we write this a bit nicer, and we get x3 is equal to 1/4 minus 1/4 times x1 minus 1/4 x4. It's exactly the same equality, we just moved the variables around. And the second equality basically stays the same, but there is a problem here because we have x3 on the right hand side, and it shouldn't be there because x3 is not 0 anymore. So we have to get rid of it. And what we do is, to get rid of it, we just plug in what x3 is according to the first equality. Right? So we know x3 is equal to 1/4 minus 1/4 x1 minus 1/4 x4. So we just plug that in, and then we simplify, and we get that the value is 1/4 plus 3 divided by 4 times x1 minus 2 times x2 plus 3/4 times x4. And this is just equal to x5. Okay, so this is our new dictionary. Now, we have 2 copies of label 4. We have label 4 in the right picture and label 4 in the left picture. x4 is on the right side of these equalities on the right-hand side, and then y4 is also on the right-hand side. So we don't want that. We want to get rid of 1 copy of label 4. So we do this on the left. We just increase this value y4. Okay? And the question again is, how much can we increase y4 until one of the other variables becomes 0? Well, we have 3 equalities here. y1 is equal something, y2 is equal something, and y3 is equal something. Which one will become 0 first? Well, y3 will never become 0 because y4 doesn't even appear on the right-hand side there. And y1 will become 0 once y4 reaches 1/3, and y2 will become 0 once y4 reaches 1/2. So the first one will happen first, which means y1 will become 0 first. Okay, so we get a new dictionary by moving y4 to the left and y1 to the right, which means we get 3 times y4 is equal to 1 minus y1 minus 3y5. Again, we don't want these coefficients, so we just divide by 3, and we write it a bit nicer, and we get that y4 is equal to 1/3 minus 1/3 y1 minus y5. And then the second equality basically stays the same, except that we want to get rid of y4 on the right side. So we just plug in what we know y4 is based on the first equality, and then we simplify, and then we write it a bit nicer, and the last equality doesn't change because it doesn't involve y4 or y1. And this is our new dictionary. Basically, it means we've moved from one vertex to some other vertex in the best response polytope. Mainly, we moved along this edge at the bottom of the polytope to the right. And we picked up label 1 in this process. So now we have to drop label 1 in the right polytope. And I need some more space to write this down. So we write a new dictionary for that. We increase the value of x1. And we do this until some other variable becomes 0. So which will become 0 first, x3 or x5? Try to pause and think about it for a minute. Right, x3 will become 0 first. So we want x1 to be on the left side and x3 on the right side. And we therefore write 1/4 times x1 is equal to 1/4 minus x3 minus 1/4 x4. We don't want this coefficient in front of x1, so we multiply by 4 the entire thing. And we get this nice equality. And then for the second equality, we make the same changes as we did before. We just write it down again. We plug in the value for x1 and we simplify. So I'm skipping the intermediate steps here. We just get x5 equals 1 minus 2 times x2 minus 3 times x3. Maybe you can take a piece of paper and do these calculations yourself just to check that everything is correct. And at this point, we realize we've picked up label 3 again. And that was the label we initially dropped, which means we've now reached a fully labeled pair of points again. We found a basic solution that actually corresponds to the Nash equilibrium. And this is how Lemke-Howson really works. So it just moves around in these polytopes, but it doesn't draw the polytopes. It just maintains the dictionaries and rearranges these equations again and again until it finds a basic solution in dictionary form that corresponds to the Nash equilibrium. Again, these polytopes could be large, exponentially large, so you might have to make an exponential number of these pivot steps. So Lemke-Howson is not guaranteed to be an efficient algorithm. However, it seems that in practice, you will very rarely encounter games where this happens. So in most cases, Lemke-Howson will give you a solution quite quickly. So as long as you only have 2 players in a game, you can use this algorithm.